Good morning, AP Physics students. It is Wednesday. This is the last day of physics class before spring break. We're going to be going over the results of your lab. We are going to be going over angular momentum, and I'm going to actually link some other videos into this lesson because I can't really show an animation, and so I'll probably try to just stick to one extra video to highlight the things that I'm not really able to animate or show you. Angular momentum is kind of an interesting topic. Anyhow, for starting off with our bell work, we will be looking at some linear momentum. And so these are both AP test questions. And go ahead and hit pause. See if you can solve one or both of them. The one on the left is a little bit easier than the one on the right. The one on the right, you're going to need a couple of equations. See if you can get them right, and then hit play, and I'll go over how to get them. Okay, let's go ahead and figure out how to solve these. The answers are going to be C and D, by the way. So if you did try them at home, go ahead and see if you got them right. All right, let's see how they're actually calculated. So let's grab a highlighter here. So this one is a Sticks. It's an inelastic collision. Inelastic collisions lose energy. So I already knew the answer was C or D, but I had to find the velocity also. So I wrote out a conservation of momentum, and after I plugged into it, I realized it was very solvable, and so I can see that the answer was 2, and that it's C. If you did not know that inelastic collisions lose energy, you could then plug in the velocities and use 1/2 mv squared. But you should know that inelastic collisions that stick together lose energy, because if you don't know that, you might actually try to use conservation of energy when you're not allowed to. So it's very important you know that elastic conserves energy and inelastic does not. Speaking of elastic collisions, this is an elastic collision, and this one you're going to need 2 equations to solve. Sometimes you only need 1 if they tell you enough information, but in this case, you need 2. But it is actually solvable. It does look kind of crazy, though. I'll walk you through this, and I'm going to do a little bit of colors here. So the first formula you have is a conservation of momentum. I'll go ahead and highlight it down here. This formula is always true as long as you have no forces acting on the system from the outside, like a strong windstorm acting on the cars, or as long as you don't have like a third car that left the system. So we just have 2 cars, so we're good to go. Unfortunately, there is not enough to solve this, and so we're going to need another formula. The other formula comes from the fact that this follows conservation of energy. Now, I know this formula doesn't look like conservation of energy. It looks like just velocities. But actually, if you go back 2 lessons, I showed you where this formula came from. This is velocity initial plus velocity final of one object is going to equal the velocity initial plus the velocity final of the second object. And it comes from taking 1/2 mv squared, the kinetic energy, and basically just remanipulating it a lot and combining it with the momentum formula. So it is a new formula, and it will allow us to solve this. We have 2 equations, 2 unknowns, and now I just need to do some substitution. So here I'll highlight, see there's that green formula right there, and here's that yellow formula right here that we're actually going and plugging this guy right into. So we're substituting out for v velocity of the second object final, we're subbing it out for the first half of the green formula. And from there, it's actually some pretty reasonable algebra. We distribute the 3m to both terms, we combine like terms, and we can see that the initial velocity the final velocity equals 1/2 of the initial velocity, and it's in the negative direction. I don't know what the other object's final velocity is as far as my math goes. Fortunately, multiple choice tests allows me to just select D because that has to be the right answer, and I can go ahead and move on. Not a very easy question, but you do need to know how to do these, and that you need to be willing to use this formula right here. It's very important, very useful formula. That's why I've been bringing it up a lot. All right, let's head into the lab. Okay, so the idea behind this lab is that you graphed this graph right here, basically. And the slope of your graph was equal to the angular momentum. And we can see that by taking a look at this formula right here, where your y-axis was w, your x-axis was 1 over moment of inertia, and the slope is going to be equal to L. If we multiply both sides of the equation by I, we can put it back into that form, the angular momentum form. And actually, the simulator had a graph for angular momentum. You probably noticed that was sitting at the same value the whole time. And that value was actually L, which would match the slope of your graph you got. The whole point behind the lab is that you notice the slope of this graph was constant, meaning that L is constant. That was kind of the cool thing behind that little activity. So we have our new formula over here. I'm going to go ahead and highlight that guy in orange. What that formula means is it means that when moment of inertia, or I, changes, W will also change. My favorite example is a figure skater. When they take their arms and they have them way out, and then they go ahead and bring them in, as they bring them in, it actually causes them to spin faster. It does. And so, in fact, in class, we have this stool that you guys can sit on, and we can bring our arms in and get you to spin faster. Unfortunately, all I can do for this lesson is link a second video that has another physics teacher talking over like a video of a figure skater, because I don't know how to quite do that level of video editing yet. But that's what caused it to happen, angular momentum. And also on the simulator, so the next question here in class, when we went over this, we had the simulator in front of everyone. So the question I asked the kids was, what happens when angular velocity, when you increase the inner radius up from 0 while keeping the mass constant? Why does it happen? The simulator shows that angular velocity goes down. Why? Because you're actually a figure skater that's taking her mass and moving it outward. So, because these two rings, the mass is equal. All you're doing is taking the mass and spreading it outward. And so that causes I value to go up, which causes W value to go down. The last question on this page, right over here, is just a little calculation of a stone tied to a string that's being whirled around in a circle. And so you can actually calculate its angular momentum. A point mass has an I value, a moment of inertia of just mr squared. We can plug in the values for that. And then W is our radians per second, our angular velocity. This formula has some interesting units. So L's units are kilogram meters squared per second, not kilogram meters per second squared. That's force, newtons, but kilogram meters squared per second. So yeah, angular momentum has kind of some interesting units, but those are the units of angular momentum. All right, so let's move on to an actual example problem of a figure skater. All right, so you have a figure skater whose moment of inertia is 100, and I'm leaving it as 100 units because I'm asking kids to actually recall the moments of the units of moment of inertia, because it's an important thing for kids to remember how to do. All right, so figure skater has, well, you guys can see the answer here. So figure skater has a moment of inertia of 100 kilogram meters per second, has 100 kilogram meters squared of moment of inertia. Let's pretend her hands are 1 kilogram each, and they have her arms have no mass. So her hands are going to be point masses. I don't want to deal with arms, too complicated. Her spin's at 3 radians per second, and her hands are 1 meter away. She's going to bring her hands in, so they're only 0.1 meters away. So what are the units of moment of inertia? Well, they're kilogram meters squared. And then what will her final rotational velocity be? And we're going to get 3.59 radians per second. So let's take a look at how this is actually calculated. So I have a picture over here. Looks a little crazy, but this is our figure skater right here. And her circular hands are starting at a radius of 1 meter, and they're shrinking to a radius of 0.1 meters. All right, so all I'm doing is I'm writing out a conservation of momentum using angular momentum. So L equals IW. So at the start of the problem, we have the I of the girl plus her 2 hands, which we calculate. Her I gave you is 100. Her hands have this I value right here. It is their mass times their radius squared, and there's 2 of them. So the left half of the formula, and then all of that is spinning at the same speed, 3 radians per second. So that's the left half of the formula. The right half of the formula, it looks the same. It's the girl and her hands, but her I values are going to change because her body isn't changing, but her hands are, specifically her I values, are changing quite a bit. And so once you plug everything in, it's solvable and you get her new velocity is higher. You should know whether your final velocity is higher or lower based on what's happening to your I values. Is your mass coming in or out? So you can kind of check your own answer. The homework question on this problem is the same question with different numbers, because I figured I'll give you something easy since you don't have that much practice with this. So go ahead and work through it. See if you can get the right answer too. Try not to just look at the answer key, but then if you're having trouble, you can go ahead and take a look at it. I will see you all in virtual school when we come back from spring break. So go ahead and be on the lookout for some emails, and see you in class on Monday after spring break. Have a nice break until then. Stay safe, guys.